Hi everyone, my name is Ruyi. Today I'm here to talk about question selection for interactive program synthesis. Let's start with an introduction to program synthesis and interactive program synthesis. A typical program synthesizer takes a specification as input and generates a correct program corresponding to the given specification. However, in practice, the specification may be incomplete, leading to ambiguity among many possible programs. To find out the target one among those programs, asking questions to the user is a common way. An interactive program synthesizer solves the ambiguity by asking questions to the user. In each round, a component in the interactive synthesizer, named the question selection function, selects a question and shows it to the user. The answer given by the user can help exclude candidate programs, and finally, help the interactive synthesizer find out the target program. Let's take a simple synthesis task as an example. This task will be used throughout this talk. The specification of this task is comprised of two parts. Syntactically, the target program is a comparison between the input and an unknown integer constant. Semantically, the target program must satisfy the given two input-output examples. Initially, there are 1000 possible programs, from x greater than 0 to x greater than 999. To distinguish between these programs, the question selection function may ask the value of p1. Suppose the answer is true, then the interactive synthesizer could exclude all programs except x greater than 0. At this time, x greater than 0 must be the target program. Since the questions bring extra burden to the user, the question selection function should minimize the number of questions. However, the performance of a selection function varies on the target program. In most cases, there does not exist a global optimal selection function. For instance, let's consider two selection functions. The first strategy is to ask the value of p1 to p999 in order. If p1 is true, the target program must be x greater than 0. Otherwise, this strategy will use p2 to further distinguish the remaining programs, and so on. In the best case, when the target program is x greater than 0, this strategy uses only one question. But in the worst case, when the target program is x greater than 999, this strategy uses as many as 999 questions. The second strategy is a binary search. The first question is p500. Whatever the correct answer is, half of the programs will be excluded. In this way, this strategy is guaranteed to find the target program with a logarithmic number of questions. In the best case, it uses 9 questions, and in the worst case, it uses 10. Now, the question is, which selection function is better? Our answer is, it depends on the prior knowledge. If x greater than 0 is almost sure to be the target program, the first strategy will be better. If all the programs have the same chance to be correct, the second strategy will be better since its average case performance is better. In the definition of question selection problem, we abstract the prior knowledge as a distribution over all programs, representing the possibility of being correct. The input of a question selection function is comprised of 3 parts: a specification, which describes a domain of possible programs, a domain of available questions, and a domain of possible answers; prior knowledge, represented by a distribution, and an interaction history, which records the selected questions and the corresponding answers in the previous rounds. In most cases, the output of a question selection function is a question to the user. However, when all the remaining programs perform the same on all questions, implying all ambiguity on the question domain has been eliminated, the question selection function is allowed to return any remaining program. The goal is to minimize the expected number of questions when the target program is subject to the prior distribution. Our first step is to answer this question. Can we implement an efficient question selection function that minimizes the expected number of questions? Unfortunately, the answer is no. We established a bijection between question selection problem and optimal decision tree, an NP-complete problem. Through this bijection, we proved that question selection problem is also an NP-complete problem. The good news here is, through this bijection, we can adopt a state-of-the-art strategy for optimal decision tree, named the Minimax branch strategy. Minimax branch strategy is a polynomial time approximation algorithm and has been proven to achieve the best approximation ratio in multiple variants of optimal decision tree. Minimax branch strategy is a greedy algorithm. In each turn, it chooses the question which minimizes the probability of remaining programs in the worst case. For example, when the prior distribution is a uniform distribution, P500 is the best question. Whatever the answer is, the probability of the remaining programs is always 0.5. When the prior distribution concentrates on x greater than 0, P1 becomes the best question instead. In this case, the worst answer from the user is true, and at this time, the probability of remaining programs is only a little bit larger than 0.5. Before applying Minimax branch strategy to question selection problem, we must address two key challenges. First, to find the best question according to Minimax branch strategy, we need to evaluate the answer of different programs on a question. However, the program domain can be extremely large. It's hard to find the best question quickly. Second, since the questions in inductive synthesis are asked to a human user, inductive synthesis has a high requirement on the number of questions. Minimax branch strategy sometimes still uses too many questions. We designed two approaches, named the Samplesy and EPSSY, to address these two challenges respectively. The key idea of Samplesy is to use samples to represent the whole program space. Samplesy uses a sampler that constantly samples programs according to the prior distribution and uses Minimax branch strategy only on the samples. A problem here is sampling is time-consuming. The user has to wait for the sampler to obtain enough samples. Our solution to this problem is parallelization. We notice that the user may always spend some time answering questions. Therefore, we let the sampler run background, utilizing the time when the user is answering the question. The figure shows the structure of Samplesy. It is comprised of two background processes, the sampler, the decider, and one foreground process, the controller. The sampler is a special synthesizer that constantly samples programs from all remaining programs according to the prior distribution. The decider verifies whether the ambiguity has totally been eliminated. Concretely, it checks whether there are two remaining programs differing on some question. The decider can be implemented by firstly using encoding techniques to construct an SMT formula, and then invokes an SMT solver to verify this formula. The controller receives samples from the sampler and selects a question according to Minimax branch strategy. It is based on an SMT solver, and it always selects the question which excludes the most samples in the worst case. We still take the previous synthesis task as an example and assume the prior distribution is a distribution concentrating on x greater than 0. In the first round, the controller will require some samples from the sampler and the verification result from the decider. Since the verification result shows that there is ambiguity remaining, the controller then selects a question according to Minimax branch strategy. Here, one best question is P1, since it always excludes half of the samples whatever the answer is. Note that there we don't need to consider the probability of the samples, since the probability has been reflected on the frequency of being a sample. After receiving the question, the user starts to think about the answer. Meanwhile, since the sampler is a background process, it still performs sampling. Suppose the user's answer is true. The controller feeds back this answer to the sampler and the decider. The sampler filters out all invalid samples, and both sampler and the decider update their internal structures. In the second round, the controller still requires samples from the sampler and the verification result from the decider. At this time, The verification result shows that there is no ambiguity remaining, so the controller directly returns the sample x greater than 0 as the answer. We proved that Samplesy is an effective approximation to Minimax branch strategy. The probability for Samplesy to select an ineffective question decreases exponentially when the number of samples increases. Now, we come to the second challenge. Minimax branch strategy may use too many questions. To address this challenge, we observe on the procedure of Samplesy and make the following observation. To ensure the 100% correctness, Samplesy sometimes uses many questions to exclude programs that have extremely small probabilities. Now, suppose the program domain contains only 4 programs and the distribution concentrates on x greater than 1. To eliminate ambiguity, Samplesy will firstly use a question on P2 to distinguish between the left 2 programs and the right 2. If the answer is true, Samplesy will further use a question on P1 to distinguish the remaining 2 programs. However, are these questions necessary? According to the distribution, the probability for x greater than 1 to be incorrect is only about 0.3%. Can we directly return x greater than 1 here? For most applications of interactive program synthesis, we believe such a low error rate is acceptable. EPSSY extends Samplesy by involving bounded error rate. The average case error rate of EPSSY can be controlled to arbitrarily small. The key idea of EPSSY is to firstly guess a program and then use questions to verify it. For example, suppose now we have those 5 samples. X greater than 0 is a guessed program, and EPSSY asks a question on P1. This question distinguishes our hypothesis x greater than 0 with the other 4 samples. Since the samples represent the general property of the whole program space, if x greater than 0 is incorrect, with high probability, it will differ with the target program on this question. As a result, it will be excluded in this round with a high probability. EPSSY utilizes the opposite of this conclusion. If x greater than 0 survives on P1, it will be more likely to be correct. This figure shows the structure of EPSSY. Comparing with Samplesy, EPSSY doesn't contain a decider, since it does not need to check whether the ambiguity has been eliminated. And Samplesy contains a recommender, which guesses a program from remaining programs. There have been existing works on finding the most probable program. Any of them can be used as a recommender. The controller of EPSSY is different from Samplesy. When it selects a question, it makes a trade-off between 2 criteria. The first criterion is that the question should be challenging for the recommendation. Concretely, the recommendation should perform differently from most samples on this question. The second criterion is the same as Samplesy. The question should be effective in eliminating ambiguity. There are 2 possible endings for the recommendation. If the recommendation survives on enough questions, which reaches a presetting threshold, EPSSY will return it as the answer. Otherwise, if it failed on some question, EPSSY will require a new recommendation from the recommender. We proved that EPSSY can reach an arbitrarily small error rate with a logarithmic level threshold. In our evaluation, we construct 2 datasets representing 2 reasonable applications of interactive program synthesis. The first dataset, named as repair, represents the application in program repair. This dataset is constructed from the program repair track in Sega's competition. The second dataset, named as string, represents the application in string manipulation. This dataset is constructed from the string benchmarks collected by a previous work. This table shows the properties of those 2 datasets. The third column lists the geometric average size of the program domain, and the fourth column lists the maximum size. We implement a random strategy as the baseline, named as RandomSY. It is an abstraction of random strategies used in previous work. This figure shows the performance of all three approaches on the datasets. The x-axis represents different benchmarks, while the y-axis represents the number of used questions. The result demonstrates that both Samplesy and EPSSY outperform existing strategies. Besides, the overall error rate of EPSSY is only 0.6%, but its performance is better than Samplesy, especially on the string check. This result shows that even only evolving a small error rate could further reduce many questions. More details can be found in our paper, including more details, or proofs, the way to implement a sampler that samples programs according to a PCFG, and more evaluation results on the prior distribution, the number of samples, and the choice of the threshold. Thanks for listening, and I'm glad to answer the questions.